Hello, everyone. In today's webcast, we will discuss chaining analysis between two powerful solution sequences, one which is in the explicit domain, and the other is in an implicit solver in MSC Nastran. Our focal application in this case will be fan blade out to rotor dynamics, which is widely used in aerospace industry. Here's the overview of the presentation. We will introduce Nastran and its new solvers, including Solution 400 and Solution 700, the implicit and explicit solvers in Nastran respectively, followed by a background discussion of fan blade out and rotor dynamics, industry's past and present practices, and then we will discuss the new solutions for this application. Finally, I'd like to review some other important chaining simulations, time permitting. Most of you have heard about MSC Nastran, hopefully. This is a product that is the premier CAE product and a de facto standard in many industries, in particular aerospace and automotive industries. MSC has world-class engineering products to address simulation needs of many industries, MSC Nastran, Mark, Adams, Dytran being the leaders in solver technology. While these products are great solutions to specific classes of problems, we do realize that our customers need a more integrated solution to improve their design processes. This is why MSC really has made significant investments to bring the technologies such as linear, nonlinear, multi-body systems, implicit and explicit technologies from different products under one umbrella, and that is MSC Nastran. By doing so, we have created an entirely powerful product to address the needs for complex, multi-physics, and multidisciplinary simulations. In addition to MSC in-house technologies, we also continue to integrate our partner technologies, which are the leaders in their own disciplines. For example, MSC Nastran includes technologies from LSTC. We have integrated Elastana into our products and solutions. Alpha Star's macromechanical failure models for composites. And Free Field Technologies, Actran, which is now an MSC affiliated company specialized in acoustics. You can expect to see more solutions made available through MSC software. By the way, MSC software will celebrate its 50th anniversary in February 2013. We are proud of our heritage as a software company for the past 5 decades. This has been a company that really pioneered and contributed to the development of engineering simulation. The team of MSC is excited about continuing to drive the future of engineering simulation going forward. One of the new solutions in MSC software, in MSC Nastran, is the Solution 400 implicit solver. It was created to offer advanced nonlinear technologies based on Mark, but was also enhanced and developed to include many more capabilities such as statics, heat transfer, coupled thermal and mechanical analysis, fracture mechanics, creep, and so on. Going forward, SOL 400 will replace traditional legacy Nastran solutions. In terms of capabilities, SOL 400 has support for large deformations, large strain. It has advanced contacts with many features, nonlinear boundary conditions, and nonlinear materials. SOL 700 is the explicit solver in MSC Nastran. It is really unprecedented technology in Nastran. It is our premier explicit solution from MSC, and it's based on two different solvers. It's based on Elastana structural solver and it's based on Dyna's fluid solver. So what we did was we took the Dyna's structural solver and we integrated that with Dyna's advanced fluid solver, and we created a very powerful product. And it is part of the Nastran solution. It has advanced FSI technology, and it supports high-performance computing environment by offering distributed memory parallel capability. It has probably more than 120 and 130 different material models to support, alloys, metals, all the way to ceramics, composites, gases, fluids, explosives, what have you. Because the structural solver is based on Dyna, we support the native output files from LS-Dyna. In terms of pre-post processing, both Powertrain as well as Team Expert support SOL700, and it basically allows our customers to use their models for explicit, transient, dynamic applications. SOL700 has many different Walerian material models and coupling methods that can be used to define and model the interaction between the structure and the fluids. The FSI capabilities in SOL700 are among the most advanced in the world, allowing an accurate simulation of the complex FSI applications, such as this bird strike example that you see here. The bird here is modeled as a fluid bird, and it gets sliced like a salami as it goes through the running engine. I hope you can see the graphics coming through okay. Then you have the hydroplaning, which is a very complex FSI application as well. The tire is highly nonlinear material. It is a reinforced material because it has a steel belts. It is inflated, and it bears the weight of the vehicle due to the gravity. And then it's rolled over on a wet surface, snow or mud. And then, you need to predict basically the footprint of the tire. Fuel tank sloshing, airbags, and blast simulations are other complex FSI applications that are also in SOL700 domain. So let's go and introduce some chaining simulations. Why do we need analysis chaining? Well, sometimes to model the real-life problems, you will need to use more than one discipline. At times, it takes different pieces of technology and physics to solve a problem. That's why analysis chaining is made possible to support a multi-physics, multidisciplinary simulation environment. In terms of type of chaining, we have the perturbation analysis going from nonlinear to linear, heat transfer, structural chaining, implicit, explicit, back to implicit integration, explicit to explicit chaining. For example, the pre-stress can be done implicitly before any other type of event. Multiple drop tests where it's basically an explicit to explicit chaining. A spring back in sheet metal forming is going from an explicit domain back to the implicit domain for a spring back. And brake Sqeal, which is a very complicated simulation, it's multi-physics, and we will touch on that later on. So with that, let's go and talk about the background of fan blade out to rotor dynamics, which is the focus of this webcast. Fan blade out and foreign object damage, they call it FOD, causes billions of dollars of damage every year in aerospace industry. A fan blade out incident on a commercial jet engine is a very rare event. However, from a flight safety consideration, it must be addressed during the design phase of the engine. the engine structure must be able to withstand these large dynamic loads generated during this type of catastrophic loading. This new generation of high bypass ratio engines with wide chord fan blades were introduced since Boeing 777, and the fan blade out has become a design condition for aeroplane structures as well as the propulsion adjacent wing structures. The Federal Aviation Administration require engine companies to perform fan blade out tests for certification, and it is the most important test and probably the most expensive one for engine certification. The methodologies for fan blade out has been evolved since early 1990s. In a high bypass turbofan engine like General Electric NX or Rolls-Royce Trent series, 90% of the thrust actually comes from a spinning fan blade in front that draws in massive quantities of air and forces it out in a ring around the engine's center, or they call it core. The primary innovations are really the fan blades. These fan blades have been reshaped to move the air more efficiently with fewer blades. And some of these blades are made of carbon fiber to save weight. And in order to keep that fan turning, a small percentage of the incoming air instead flows into the core, where it passes through two compressors. It mixes with fuel and ignites in a combustion chamber. That combustion powers the turbines that drive the fan up front. It's awesome technology. We tried to play some real live tests for fan blade out certification tests, and I hope that this comes through. But you can find many examples like this on the YouTube or on the web. What I like to play is the Rolls-Royce Trent 900 engine certification. I don't know if you were seeing the movies or not. Hopefully you're able to see it, but what you see here is a blade that is released and is impacted by the trailing blades, and it causes a very large dynamic forces and heat, and because of the unbalance, the blades start rubbing against the containment structure, and they start rubbing against the fan case. In this particular test, the engine actually passed the test because none of the blades cut through the containment structure. Currently, the containment design is largely based on the test and empirical methods, but there is a strong motivation on the part of the jet engine manufacturers to develop numerical methods that can be used to help in the design process of fan blade containment systems, to reduce the cost of testing and increase the confidence, increase the reliability of the design, and so on. As shown in this video, you can see a full engine testing can be very costly. A number of research and commercial computer programs are available that can simulate the bird strike and fan blade out on the engine case. These are generally transient, explicit finite element codes. The code themselves are accurate and have been validated by years of use, but the simulation of the sequential event, what you see here, during the entire fan blade out, starting from the blade release, impact and failure, contact models, unbalanced forces, windmilling, and the CFD effects require really a multidisciplinary environment that are still subject to active research. This is a very important chart since it will demonstrate the steps at which we need to take to do a full run fan blade out to rotor dynamics simulation. There are basically three stages. The first stage, which is here, is a pre-stress analysis of the running fan blades. This stage can be best modeled by an implicit solver. The objective here is to compute the stress and the deformations of the blade because of the high rotational velocities prior to the fan blade out and transient response in the second stage. In the second stage, which is a short duration, falls in the explicit domain. Here, the event is basically completed after 2 or 3 revolutions of the blades and lasts basically a few milliseconds. So here you'll see a large dynamic loads at a very short period of time. The last and the final stage is the rotor dynamics that is also a steady state and is primarily an implicit domain. In the next few slides, we will discuss the first 2 stages up until the rotor dynamics and the unbalance calculations. In the third stage that we will cover when we introduce the new solutions. So let's talk about the current practices. We know that the detailed explicit models are created for the fan blade out event, and simplified implicit models are constructed for rotor dynamics. Here you see a typical integrated engine with containment structure. You don't see the shaft, the blades, but they're there, trust me. It's rather a small model for explicit analysis compared to what is actually being used by engine manufacturers for fan blade out and FOD applications. The figure to the right shows a schematic of rotating shafts of the engine. To run a fan blade out or a bird strike simulation, first a pre-stress run is made to compute the stresses and the deformations in the blade. This can be done implicitly. SOL700 has an implicit solver also, which can compute the residual stresses and save the results in a file that can be read as initial conditions for the fan blade out simulation itself. Here, we switch the solvers from the implicit solver back to explicit solver in SOL700. What we'll get from the explicit analysis on a full engine model like you see here are the forcing functions such as unbalanced forces due to the lost blades, released blade impact on fan case, seizure torques, and the thrust drop. As mentioned earlier, explicit codes have been very effective in predicting the damage and the loads created from a bird strike or a fan blade out analysis. Here it shows that the fan blades, as a result of the bird impact, which is shown on the top right. So the bird goes through the running engine or running fan blade, it gets diffused, the blades are broken, and they become projectile, they hit it in fan case. You can see the deformations and all that. Here, what you see is some simulations versus tests, explicit codes such as Ditran, SOL700, Elastino, all have been very effective in predicting the damages of the engine, and they've had good correlation with the test data. This particular one shows a Ditran simulation of the bird strike on the fan blades. As the blades are released and are impacted by surrounding structure, you can also predict the secondary impacts and the damages inside the engine. Again, here the simulation accurately predicted the area of the damage that had good correlation with the test data here. And you can see, the test versus the simulation. Another one is the low pressure shaft rubbing. What they look at is the rubbing of the shaft as a result of the unbalanced forces that causes some damage to the rotor shaft. As well as the calculation and the computation of the fan blade to fan case tip clearance, which is also a design consideration, as well as the buckling of the buckling of the bearing inside the engine. To summarize the current practices, what's been done in the industry, and we know that all these codes basically do a good job in predicting the damages. We can summarize that the methodology for generating full engine model for explicit transient dynamic has been developed very effectively. Methodology for validating full engine model prior to the fan blade out for different bird sizes also have been developed. Key processes for testing, like fan blade root strain, release blade trajectory, fan tip clearance, engine mount loads, these are all fully calibrated. Another thing that I need to basically point out as far as the current practices are concerned is that the way the loads are generated. These are typical fan blade out loads that are really simplified and normalized based on the empirical data or explicit simulation. These loads are developed by engine manufacturers, and then they're passed on to the airframe companies for rotor dynamics. The unbalanced loads are applied at the fan location. The seizure torque caused by engine deceleration is applied as tangential forces to the engine wings and case. And the thrust load is applied at fore-aft direction in the engine case. The actual fan blade out models are not shared between the engine manufacturers and the airframe companies. There's a variety of reasons for that. It could be due to the confidentiality of the model, reliability issues, or other reasons. What's being shared are basically these loads. Once the loads are provided by certain type of engines to airframers, then they will construct a very coarse finite element model for rotor dynamics, and then try to estimate the areas in the fan case where these loads are actually applied. So what they usually do, they take an arbitrary parameter around the fan case and apply these loads uniformly. So let's talk about the new solutions. To introduce the methodology for the new solution, we use an actual example. What we already discussed is the first two stages of the fan blade out and FOD simulations. That is the pre-stress simulation of the blade that is done implicitly, followed by the fan blade out that is performed explicitly. We don't need the engine casing for the first stage to pre-stress the blades. So we just use the blades, hub, and the shaft here. Then we proceed with the fan blade out in the second stage. And then after that, we go one step further. What we would like to do now is to pass on the results from the fan blade out simulation to an implicit solver for rotor dynamics. What's unique about this solution is that we will use the actual loads generated from the second stage from the fan blade out analysis, primarily the impact loads and the rub loads as a result of the blade impact and rubbing against the fan case or the containment structure. These loads can be literally in millions, and they're all transient. Second, the models that are used for fan blade out and rotor dynamics are completely different in terms of mesh density, for example. It's the same engine model, just remember that, but in terms of the fidelity, they are quite different. The fan blade out models are created by engine manufacturers and are really elaborated finite elements models. A 2 to 4 million element engine model can be very typical in this industry. Whereas a typical rotor dynamics model constructed by airframe manufacturers is less than 50,000 elements and perhaps even much smaller when a super element dynamic reduction is performed to reduce the size of the analysis matrix. In our example, we can pre-stress the blade using SOL700 implicit solver in the first stage by applying a full RPM. In the second step, the fan blade out. For the fan blade out analysis, we run the simulation for about 3 revolutions, about 8 milliseconds. And in the final stage, what we do instead, we output the actual blade out loads, thousands of transient loads, if not millions, into Nastran master database. To honor the confidentiality issues, the model information is not written to the database. So actually, the engine companies can take the Nastran database and just pass it on to the airframers without any worry. This is the Nastran database that includes the actual realistic loads passed on to the airframers. So in the next and the following step, the airframers construct a coarse mesh of the same engine for rotor dynamics using SOL400 implicit solver to simulate the rotor dynamics effects. And now I will explain how this solution 400 is used to manage these loads for rotor dynamics and unbalance in the upcoming slides. In fan blade out example, our engine model has a few thousand elements that include the fan blades, the shaft, the bearing models, and the containment structure. The fan blade out model has about 8,500 nodes and 9,000 nodes and about 8,000 shell elements, and is deemed to be sufficiently detailed to capture the physics of the problem. Again, this is only a simple example to make sure that we can include that as part of our tutorials and documentation. We didn't want to construct a 4 million element model here. The fan blades were constructed by shells with various thicknesses across the width and the length. The rotor was made with a hollow rod with valid cross-section across its length and has a rotational velocity of 4,500 RPM. The material for both the blades and the rotor is titanium grade. The bearings were modeled by constructing 2 concentric rings with predetermined stiffness properties that can contact each other. The flange on the bearing prevent the axial movement of the rotor during the fan blade out. The bearing models and their properties are important design consideration to simulate the fusing during the fan blade out and rotor dynamics analysis. Fusing is basically an event where a bearing or other support structure fails as a result of high loads beyond the design strength of the fusing structure. Basically, the stiffness drops to 0. To come up with the stiffness of these bearings, we had to do a trial and error to come up with the right stiffness as required in the design. So we were monitoring the force displacement characteristics. So here we show the fan blade out analysis with one release blade at 1.49 milliseconds. So you can see this blade is being released. The purpose of this fan blade out analysis is basically to ensure engine safety and comply with FAA and JAA, the European counterpart of FAA, the Joint Aviation Authorities regulations. The simulation computes the dynamic load and predicts the damage to the fan blades, fan case, containment, rotor, and other components, like the slides that you saw previously. Usually, the analysis is performed to capture the behavior of the engine for up to 3 revolutions. They usually do not run more than 2 or 3 revolutions. Even though longer simulations are prohibitive due to the massive amount of data to be stored and excessive run times, sometimes it's necessary to run the fan blade out as long as 10 revolutions. And they do that to basically partially correlate the explicit results to those of rotor dynamics analysis. Three primary dynamic loads are computed and stored in the Nastran database. These loads are: one, impact loads. This is when the release blades, like you see here, acts like a projectile and hits the surrounding structures. Two are the rub loads on the fan case. Rub loads occur as a result of the fan blade tips coming into the contact with the inner surface of the containment ring and or its trench filler materials. Three, the rub loads on the blade tips. So all these loads are computed and they are stored in the database. This slide shows the steps that we go through the fan blade out using solution 700 explicit solver and then using solution 400 for rotor dynamics. If you notice, you'll see that the fan blade out model here is a lot more finer than the SOL700 rotor dynamics model as shown to the right. This is intentionally constructed to demonstrate how the process works. Once the loads are computed by 700, typical impact loads and the rub loads that are shown here, they will be written in the master database. Next, in the solution 400, which is used a different, much coarser mesh of the same engine. This is mimic what actually happens in the industry. We take those loads, and then the first thing that SOL400 does, it reads all those loads that are in the database and maps them automatically on the coarse mesh. SOL400 has a unique search and mapping algorithm that searches for the closest elements and the nodes on the engine, and then it maps those loads to the closest elements on the nodes to the load locations. This way, the rotor dynamics will have the right loads at the right location, applied at the right time. That is really the uniqueness of this solution. (400) has the same rotor dynamics capabilities as the legacy solution 129. Some of you may be familiar with Nastran rotor dynamics solution, but it's even more powerful. So it can be used to generate the whirl diagrams or the orbit diagrams and the time histories of the interest. Some notes on the rotor dynamics model. Rotor in this simulation is replaced by a stick model using beam elements. The rotor dynamics simulation involves basically both rotating and stationary structures. But currently, Nastran rotor dynamics analysis requires that the rotating portions of the structure be modeled as central line or stick models. In this analysis, in this example, the sectional property of the stick model was computed based on the hollow shaft rotor of the explicit model. The stick models basically can be obtained using Gaussian reduction or classical lumped mass technique. The figure on the right is a representative shaft model in the rotor dynamics analysis using beams. Then the fan blades also are replaced by a bunch of RBE3s. In Nastran, we have multiple point constraints, and RBE3 is a special version of the generalized NPCs, and it represents rigid spokes. So the fan blades are automatically replaced by these RBE3s. These rigid spokes are generated automatically again in 400 based on the data which is stored in the master database. Mass, inertia, and offsets are added from SOL700 to a new entry in SOL400 called unbalance. These variables are printed out in the SOL700 output file. Fusing was added with the C-bush element at the bearing locations. SOL400 supports a special element to predict the behavior of fusing when the bearing fails. This is a phenomenon when the engine stalls due to a seizure torque and causes a large bending force on the shaft, resulting in bearing failure. The rubbing forces at the blade tips are also summed up to compute the torque which is applied to the rotor. Advanced search and mapping, again, is done in 400 to distribute the fan blade loads in the right location and the right time of the rotor dynamics model. And because of the time step differences between the implicit and the explicit, we use fast Fourier transformation to basically go from the time domain to frequency domain and back. What you see here shows the forces drop to zero when they fail during the fusing. Basically, there's no stiffness anymore. In the implicit rotor dynamics analysis, bearings can be really conveniently modeled using Nastran C-bush elements, where the stiffness coefficient can be directly input. C-bush elements are generalized spring damper elements that can be used to represent bushing connections. C-bush elements support material nonlinearity in the forms of force displacement curves for nonlinear stiffness representation, and as well as force velocity curves for nonlinear damping representation. The new capability in C-bush elements, you have the fusing capability that can be defined with various failure criteria. The user-specified failure criteria includes ultimate loads, maximum relative displacements, in tension, as well as in compression. Going forward, as far as the future is concerned and the development roadmap, we're working on to recovering full system engine loads beyond the initial revolutions, not just the blades and the surrounding structures, but everything. We are looking for methodology to capture all the damages and map those from explicit to implicit. We are working on improved boundary conditions and damping models. And probably most important, we're really working hard on performance, leveraging the high performance computing. The industry is asking us to speed up by 1,000% or 1,000 times, because you want to reach to the day that you can run that 4 million element or 5 million element model all the way through the windmilling explicitly. And so the speed, performance, and the data storage becomes key. So why we developed this methodology? This was actually based on customer requests and members from our Rotor Dynamics Consortium. Our customers were basically consisted from big aerospace OEMs and their tier 1 suppliers. They were telling us that both methods, implicit and explicit, have their own strengths and weaknesses. So basically, you need an implicit-explicit chaining to complement its solution. For example, the implicit code assumes that the rotor is axisymmetric, right? But whereas it becomes totally non-axisymmetric as soon as the fan blades gets released. On the other hand, the explicit solvers have very small time steps, and it is really impractical to run the entire event for many seconds, especially with a few million element model. That's why we came up with this methodology to address what customer needs and streamline the engine certification. So in summary, we have a YouTube presentation that we created for the tutorials for those of you who are interested to see a very short, sweet summary of this entire event. You can go to MSC software website and search for fan blade rotor dynamics video, or you can go on YouTube and look for it. This is a very popular video. Last time I checked it, it had more than 10,000 hits. In 5 minutes, you can basically capture the idea. For more details, we have published a paper about this solution. It was presented by one of the co-authors from Boeing. It's an AIAA paper, and the title is An Efficient Multi-Disciplinary Simulation of Engine Fan Blade Out Events Using Nastran. Oh, I skipped the last slide. Even though this webcast was focusing on fan blade out rotor dynamics, I think it's noteworthy to also talk about other chaining applications. There might be other webcasts elaborating on other applications. One of those applications is brake squeal. But what is brake squeal is a distinctive high-pitched noise caused by friction-induced dynamic instability. Contributory factors are forces at the disc pad interface, temperature, caliper stiffness, variation of friction coefficient, disc rotational speed, and deceleration. Other variables in brake squeal may include damping layers, dust accumulation, piston pad, contact condition, grease, and what have you. This is another application which really deserves its own webcast to discuss the details of the analysis chaining. As far as the chaining applications are concerned, the sheet metal forming is another one where the pre-stress is done implicitly. Deep drawing and the sheet metal forming is performed explicitly, and then you can switch from explicit back to implicit to simulate the spring back effects by using analysis chaining. I hope that you found this webcast presentation productive and beneficial. I'll pass on the control to Srinivas with your questions.